Greetings and welcome to a new video about half-wave rectifier. In this example we'll discuss again a controlled version of the half-wave rectifier where we use the Thyristor to control our signal. This will be an RL load. In this case we have discussed in the previous example of a resistive load, so we will extend now the operation of this half-wave rectifier. Of course we will see everything step by step in our calculations and verify these in MATLAB Simulink simulations. Now this is the objective or given. We have the input voltage Vs of 200 sine 100 pi t. The frequency is 60 Hz and the amplitude is 200 volts. The load will be a series combination of resistor and inductor, so 100 ohm resistor and 200 millihenries for the inductor. And the circuit is actually shown here, and we have also this Thyristor here with the gating signal, which will be then at the 25%, which is given as alpha. We will apply here a signal. Again, the input signal is here, and we will measure the voltage across the complete load here, and we'll also look at the load current. So what we want to calculate is the following. We like to calculate the average load current for this situation, the average load voltage, then the RMS load current, and also the RMS load voltage. Then we'll look at the absorbed power in the load and the power factor finally. So let's go one by one how we can do the calculations for this example. Now before we jump to the actual calculations in detail, let's also look at the waveforms. This is the waveform for the input. You see here the horizontal axis is not given in the time but in the omega t, which is convenient for our calculations. You see it is starting at 0 and then going to 2 pi, but that's then the full period. You also see here the maximum, which is the Vm, which is in this case 200 volts. Now we also see here the Vt, which is our Thyristor voltage. Now in this case you see here the alpha, which is the delay angle, also called the firing angle. Now until that time the Vt, which is the Thyristor voltage, is actually following the input voltage. And then when it is fired, it will then become 0 and it extend up to beta. We will discuss this, why it is going further than the pi here in this case. Now for the load voltage, we see here the blue one. It is actually coming up after this alpha. So actually the combination of this pink line and the blue line is together actually our red line here. And again, you see here the same situation where you have the output voltage or the load voltage is going further than the pi, which is up to beta. The final one, which is our load current, which is now in this case going from alpha up to beta. And this distance, it is also called the conduction angle. And I'll repeat the process, of course, after this 2 pi, and then you can again get the same operation for all cases. Okay, let's now go to the calculations. We need to have a delay angle of 25% and other parameters we need to use and calculate these 6 unknowns here. Okay, we start first with the input voltage representation. We start by converting the t into omega t. And that's shown here again. The Vm is 200 and the omega t is in total 120 pi t. So omega is 120 pi radians per second. Now for a forward biased ideal Thyristor, the differential equation can be written as follows. So we have the input, which is in this case Vs, and then we have our output, and we have then the following two parts of the output, which is then the resistor and the inductor voltage. It's actually shown here using Ohm's law. Now the solution for the load current, in this case that is what we want, is the sum of the force response, which is given by here, comma forced, and also the natural response. In mathematics, this is also called the homogeneous and the complementary solution. So we have actually now two parts will be added together because we have here a linear equation. Now, force response is given by this expression. This is the expression for the response in the forced form, and this is the natural response. You see again here the alpha is appearing, and also the other parameter we will discuss shortly, like the z and the theta, and also here the tau, which is our time constant. And when we take this together, we will get actually the total expression. You see here now the force response plus the natural response. So take them together, you see here again in more detail from this. When you now combine them together because they have similar parameters like the Vm over z, so we can take it out, and then you have this expression. Now here again, we see the z, which is our impedance, as the absolute value, which is then the square root of the resistor squared plus the reactance squared, actually, which is here then omega L of the inductor. The theta is the arctangent of the omega L over R. And we also have a time constant, which is then L over R. Okay. And then if you now do that and also convert the t into omega t, you have actually this expression here. Now in total, the load current can be then given by this expression. You see here again the expression we have determined, which is valid between alpha and beta, which is our conduction angle. And it will be 0 between beta and 2 pi plus alpha. So in total you get here actually the period of 2 pi again. Now in summary we can say the following. Load current will stay 0 until this delay angle has been reached. So if that is reached, then we start actually to increase and become positive. That way is then the thyristor is off, always reverse bias until that alpha. So until we fire this angle or give it a signal at this gate node, then the thyristor will be conducting and then you get the current flow. The load current becomes then positive at that delay angle, alpha, and the thyristor will be then forward bias, which is then here called on. The load current becomes again 0 at the another angle, which is called the extinction angle beta. In this case, we always have between alpha and beta where we have our positive load current. So load current doesn't also not flow during the portion where we have the positive cycle of the AC signal, because if you look carefully, this part is the positive cycle between the alpha and the pi, but it's actually going further, right? That's why we have this name of extinction angle, which is going a little bit further than that, so not pi but beta. And that is also interesting to see in the plot of the load voltage where you see this negative part, but the current is still positive. So the stored energy, that's actually the reason for this, is the stored energy in the inductor maintains the load current and the inductor terminals will be then reversed such that the current will be then flowing in the direction as before. And then the thyristor will be then also kept forward bias and conducting. This is similar to the situation where you have a diode here and again there are a load. The same situation will happen here. It doesn't start at alpha, but at 0. Let's go to the next part, which is our extinction angle beta. This is an important parameter because we need to determine it. We know the alpha, but we don't know the beta yet, and that is important for the calculations. Now that is the point where you have the load current also 0. So there are 2 points where the load current is 0, at alpha and at beta. So we can say if I now get this equation here, and if I now equate that to 0 and evaluate that at beta, I can determine the equation to determine the beta. And that's done actually here. So we take this completely part and then substitute here for the omega t, because that is our variable, beta. So here you get the beta, it's actually this here, and then you equate it to 0. Now you can divide out this Vm over z, then you get this expression which is easier to use, and we can now solve this. You can use that using your solver numerically, and then once we know of course the delay angle, we can do that. If you don't know the alpha, we cannot do that. So if you know the alpha, and you can give now the solution for the beta here using this expression. By the way, the beta and the alpha are all in radians and not in degrees. Okay. So again, our delay angle is 25 degrees, but we need to have it in radians, I must say. That means then we need to convert this degrees into radians. That's done by 25 degrees times pi over 180 degrees. That will then be here 0.436 radians. Now we can determine again this beta by solving this equation. We will do that. So from the given information, we already know that the z will be this, because that's 100 squared plus 120 pi, that is the beta, times 0.2 from this inductor. And that will result in 125.2 ohms. The theta will be then, again, omega L over the resistor, and then arctangent of that one, that will result in 0.646 radians or 37 degrees. And you have here also this time constant, which is then 0.2 henries over 100 ohms will be then 2 milliseconds. So we have now the necessary information in order to use this formula. So then we have the following. The complete expression here for the load current will be then given as 200 over this impedance and times this sine of omega t minus the theta, which is determined, and then minus the sine of the given alpha here, because that's here the delay angle, again minus the theta, times the e to the power, this expression where you see the alpha minus the omega t, which is our variable, divided by omega times the time constant, which is actually shown here. Okay, now we have also this expression in a more convenient way, because we can work out this 200 over 125.2, etc. So all the parameters here, this is also just a number, because sine of 0.436 minus 0.646 in the sine is just a number, and then with the minus sign will be probably here, and then plus. You can also convert that, because 1 over this 120 pi times 0.002 is actually 1.326 times, in the parentheses, this expression in the numerator and the exponent of the e. And this is only valid between alpha and beta. Okay. Now we have our expression for the load current, which is now can be used for calculation of the other parameters in this example. Okay, we go first with the average load current. Now, for that we need to use the formula of the average value, because this is 1 over the period, and then we start at the point where the current is becoming positive, and then up to the point where it is again 0. That's actually between alpha and beta, and we need to use the load current expression as shown here. We know the alpha, that's just given, but we don't know the beta still, but that's need to calculate it by using this formula. So again, taking this formula and now substitute here the theta and the alpha we have here, and also the values we just determined. When you solve this problem, you get here beta of 3.79 radians. Okay, that means we can now solve this, substitute here the alpha and the beta, and use this expression in your calculator or in the solver as shown here, and that will result in 542.1 milliamps. But you can also do it faster. If you know the alpha and the beta, that is actually sufficient, and of course also the given amplitude for your input signal and the resistor. Now this is more convenient to use, so if you know this, you can just go right away and don't need to do the integration. So if you do that, you get also 542.1 milliamps, so it's actually the same. Okay, let's now go to the next step, which is our average load voltage, which is the B. And that is given actually by this expression. Why? Because this is the average load current. And using Ohm's law, we can say average load current times the resistor. Then you will lose the resistor in the denominator, will be this. So it's actually pretty simple. That's actually just this. So you can actually take also this value and then do times 100, the exact same procedure, and then you get here 54.21 volts. Okay, so we have again the nice and simple result from this equation. Now question C, that's the RMS load current. Now how do we do that? Again, using the expression for the RMS value, the square root of the 1 over the period, and then again starting from alpha to beta, and then the quantity squared, because our expression is shown here, and that is then actually shown here. Again, we know the beta, we know the alpha, we know the expression. Square it, of course, more cumbersome, so we can again use a solver to do that, and that will result in 830.2 milliamps. Is there also a faster way to do this? Luckily, yes, and that's this expression. You see here the Vm, the Z, so we need that. We also need, again, the beta and alpha. And you can now actually use this formula. Again, I won't drive this formula, but you can use the formula instead of integration using the calculator or the solver. And that will result actually in the same RMS current here, RMS load current. So you see here actually where we do the alpha, beta, and theta. That's actually all here. So it's also nice. So we have again the same result using two different operations. Next one is RMS load voltage, which is actually shown here. Again, the same expression. But now we need to look at the load voltage expression, which in this case, if you look at the blue line, which is following from alpha to beta, exactly this red line, which is our input. So we can say, instead of load voltage, we can say it is the source voltage. That's actually shown here. And the source voltage is actually shown here, and then using in the omega t domain, we can just say this Vm and then sine omega t. That's actually shown here. And again, we use the Vm as 200. Now, when you solve this, again using the alpha and the beta, you get here 101.8 volts. Is there also a simpler formula for that, using this similar expressions without this integration? Lucky there is, and again I won't drive the formula, but that is actually here. You see again, you need the amplitude for your source, you need the beta and alpha, and you substitute that in this formula, you get now also exactly 101.8 volts, which is of course very nice. So it's up to the calculation and also what you want. For this specific case, of course, you can use the formula or you can do the integration and get the same result. Okay, now we have now the A up to D, and now we need to look at the observed load power and then finally the power factor. For observed load power, we need to use the RMS load current squared times the resistor, not the RMS load voltage squared over resistor or the impedance, because it's really about the observed power, and that happens only effectively in the resistor, not in the inductor or any reactive component. So be careful about that. So use this value and square that, it's the RMS load current, times only the resistor, not the impedance. Okay, then you will get here 68.92 watts. The power factor is defined as the load power divided by the apparent power. Apparent power is the power delivered by the source, which is in this case just one source, which is then the RMS load voltage, times the RMS load current of that source. So it's actually this current source. Now this source from the current is exact same as load current, because the thyristor will conduct only when the gate is fired, and if it is not conducting, then there's also no source current. So we can say in series they are the exact same, so we can just copy this value. But for the source voltage, it is just 200 volts as the peak value, because it's the pure sine wave, and you divide by the square root of 2. That's the famous formula, and then you get here 141.4 volts. Now taking this together and just multiply these two, you get here 117.4 volt amperes as our apparent power. Now substitute that in here from the question E and from this, and you get here 0.587. Good, now we have done everything. Let's now verify these in the simulations. First we start with the Simulink circuit results. This is the Simulink circuit. You see here the AC volt source, this one. This is the thyristor. This is the pulse voltage source where we actually apply this alpha. We will see the details shortly. I also have some meters, the voltmeter here to measure the voltage across the thyristor, the voltage here across the complete load, the current here in the load, and also the voltage of the source. So I also put it in the scope. I will also present it shortly. I also calculate the mean value and the RMS value for the load, current, and the load voltage. Now let's go one by one. You see here the average load voltage, which is 54.21, which is indeed as we have calculated, so that's correct. The RMS load voltage is 101.8 volts, also as we have calculated. The average load current here is 0.5421, which is then 100 times smaller, because you just divide this by 100. And here the RMS load current is also given here as 0.8302 amps, or we had of course 830.2 milliamps, so it's also exactly as we have it. Now in more detail about this pulse voltage source, you see here this description. You see here this pulse time delay TD, which is calculated using 25, which is our alpha, by 360 degrees, and also divided by the frequency in this situation. And that will result in this time of 1.1574 milliseconds approximately. So you don't type here 25 degrees because the units are in seconds, so you need to really convert that from this radians or degrees into the seconds. I also use the rise time and the fall time close to ideal, so I just picked here very small values like 1 nanoseconds. And the pulse width I have chosen as 1 millisecond because I want to only give it a short pulse and then it needs to again disappear. So it will give the gate signal after 1.1574 milliseconds and it will last only for 1 millisecond and then come back, and that's actually the whole operation here. So we have achieved our goal actually by verifying that in the Simulink. You see that also these 4 values are correct up from A to D. Now how about the waveforms in the Simulink plot? Let's also look at that. The red one here is the source voltage. The green one is our Thyristor voltage. The cyan color or light blue color is our load voltage. And the yellow one is our load current. You see here there's 2 labels, 1 and 2. That's for the Thyristor voltage. I would like to discuss it in more detail. You see here the 1 and the 2. The second one. The first one is actually at 1.157 milliseconds because there you see actually that the peak value is appearing and it will then jump to 0. That is also our alpha, because if you calculate that from this time using the omega, you'll get approximately 25 degrees, which is also our delay angle. So it is indeed correct. It is firing at the correct angle. The next one, which is this second label, which is at 0.010 seconds. And then you see it actually still at that 0 level almost. That is actually our beta. If you do the calculation here again, a similar form, you get here 3.77 radians. And we had calculated 3.79 radians, so very close to actually what we have calculated. So this is the beta. You also see again, as we have discussed, the input voltage is positive between 0 and this pi, but the load voltage is also here negative going down between the pi and beta. That's actually this part, but the load current is still positive. That is the effect of this inductor's magnetic energy stored in this circuit. So we can say everything is verified and according to the calculations, and we have also seen that in the Simulink circuit also. Alright, it was our example considering the half-wave rectifier controlled by a Thyristor, and we have seen how we can use the delay angle to calculate the required component values and the parameters in this circuit. Of course, we will discuss in more detail other rectifier circuit like the full-wave rectifier in the coming video, so stay tuned, and if you have any questions, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.